Hi all, and welcome to another video. This video is going to talk to us about electronics, and we're going to use that for the next couple of units of learning that we're going to do. So just want to talk about the basics of electronics, where it comes from, trying to think about what it might look like and how electrons experience different types of charge and so on, a bit of maths associated with it, and then we're going to do a bit of a quiz after that. Okay, so this is kind of very basic stuff. So we're going to get straight into it. So there's three terms that you really need to know when you're talking about electronics. One is voltage, one is amps, and one is resistance. And these are all measures of something. So if I was to measure the length of something, I'd measure it in meters. If I was to measure the weight of something, I'd measure it in kilograms. If I was to measure the speed of something, I might measure it in kilometers per hour or revolutions per minute. So it depends on what I'm looking to measure, and depends on the units. So these are all different types of units: volts, amps, and resistance, and they're all a measure of something. So if we imagine that electricity is a tank of, if we'd imagine that electricity is water, and the flow of electricity flows like water. So no more than water flows through a pipe, electricity flows through a wire or a cable. And I suppose the best way to think about these things is to think about voltage as being, so on the left hand side here, if we look at the tank at the very top, the tank at the top, it contains a lot of water. And if you would imagine that that tank was very, 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 very high, and the pipe was whatever size the pipe was, well, the higher that you put it, the more pressure that would come through the pipe. So the higher the voltage, the more electrons push through the cable at a certain time. So voltage is the full official title of voltage, or the definition of it is, voltage is the difference in charge between 2 points. So again, if that tank is higher up from the pipe, that'll mean that there's bigger voltage. If the tank was lower down, well, then there'll be less voltage. Okay, so voltage is basically looking at how much, I suppose, pressure, or how much difference in charge between 2 points. Okay, so voltage. Voltage comes from a unit of measure which is from Alexander Voltaire, who was basically one of the first guys to invent the battery. Amps. So amps is the unit of measure of current, and it's basically looking at current. The definition of current is the rate at which charge is flowing, and it's measured in amps. So the rate at which charge is flowing. So if I take the same two tank diagrams, and I was to imagine that the electricity was water, and if I was to have a thick pipe on one side and a thin pipe on the other side, you'll see that there's far more pressure, built up, because the pipe is bigger. Okay, so there's far more water flowing because the pipe is bigger. Okay, so if you can imagine, like, if you have a pipe which is 50 millimeters in diameter versus a pipe which is 5 millimeters in diameter, it's going to take that amount of electricity, that amount of water, to flow out of that tank 10 times faster with the bigger pipe. Okay, so current is the rate at which the charge is flowing, and this is measured in amps. The next thing then is a thing called resistance. And resistance is basically a material's tendency to resist the flow of charge or the current. Okay, so depending on the if you were to think of it in a water analogy, and the way I always tell people about this is, if you take a hose pipe and you were to turn on the tap and the water's flowing through the hose pipe, and you were to stand in that hose pipe, if you're standing on it completely, the water would stop. So there would be 100% resistance. If you take your foot off it slightly, there would be a little bit of water will go through. Okay, and if you take your foot off completely, the whole amount of water that should go through the pipe will go through. Likewise, if you were to take a hose pipe and you put your finger over the end of it, the water would reduce, but the pressure would increase. Okay, so it's creating a resistance. There's less water that's coming through it. Okay, so again, resistance is the material's tendency to resist charge. Okay, so those three terms, voltage, amps, and resistance, they're all units of measure. And we'll need to be able to state those back in terms of what a unit of measure is for volts, for current, and for resistance. Okay, so if we look at changing the voltage, so if I was to take the picture on the left, start from the left and work my way over to the right. This symbol here is the symbol for a battery. This symbol here is the symbol for a lamp bulb. And this here is a measure, an ammeter. So that's measuring the flow of charge. So if I was to take that battery there is one cell. So you can see that's 1.5 volts. Okay, so one single battery, a AA battery that you put in the back of your controls, that's 1.5 volts. So it's one battery. So we can see the light is that shade. So there's a certain amount of light coming out of that bulb. If I was to take two batteries and put the two batteries side by side, I would have 1.5 volts plus 1.5 volts, and the battery, the charge would flow around and it would make the bulb twice as big, as bright. Okay. Now also, as I increase the voltage, I increase the flow of electrons. So instead of having 0.1 amps flowing through with 1.5 volts, I have 0.2 amps flowing through with 3 volts. Okay, and that's what happens when I put 1, 2, 3 batteries in series, so one after another. That's 1.5, 1.5, 1.5, that's 4.5 volts. If I put that down through, what has happened? The wire in the battery, or the wire in the bulb, the filament, okay, has burned out because it's not able to take that amount of electricity flowing through it. So 3 amps of current, 0.3 amps of current would blow up the bulb. Okay. Now, if I was to take and change the current, I can see what happens now. So if I was to take a single 1.5 volt battery, okay, one single cell, and I was to put a variable resistor in front of it. So this is your foot on top of the pipe analogy. If I was to press down that completely, it would be completely off. If I was to let it up a little bit and allow 0.2 amps flow through, then the bulb would be weak. If I was to let my foot off a little bit more, I would be able to allow more current flow through, so 0.4 amps of current flowing through, and the bulb would get brighter. If I was to take my foot off completely and let all the charge from the battery flow through, you'll see that I'd have 0.5 amps and the bulb would be at its brightest. Okay, so an example of that, a good example of that would be if you were to take a light dimmer switch in your house, you're to turn it down. The more resistance equals the less flow equals the duller the light. Similarly, in your car radio or your radio in the house, if you turn a knob to turn the volume on and off or up and down, if you turn the volume completely down, it's turning the resistance up, which reduces the amount of electricity that flows through it. So as a result, you don't hear as much. If you higher the radio up, you're reducing the amount of electricity or the amount of resistance, which increases the amount of electricity, which makes it louder. Okay, so that's pretty much that. Okay, so and that is the exact same in terms of changing the current. We change the resistance by changing the current. Okay, now let's have a look at Ohm's law. This is the maths part involved in it. So we need to know this equation: V I R, and we look at it. We draw it like that in an equilateral triangle. So I'll draw an equilateral triangle, all sides the same. Put V in the top vertex, I in the left vertex, and R in the right vertex. Okay, and basically we can derive all these formulas from this. So if you wanted to find out what the current was, if you wanted to look at what I was, you put your thumb over I, and you'd say I is equal to V divided by R, or V over R. If you're looking to see what V would be, you put your finger over V, and then it would be V is equal to I by R. If you're looking for what R would be, you would put your finger over R, and you'd see R is equal to V over I. Okay. Now, where that happens, I is equal to current, V is equal to voltage, and R is equal to resistance. Now, the units that we would use to say it when we calculate that out. So, if we're looking for the current, the unit would be amps. If we're looking for voltage, the unit would be volts. If we're looking for resistance, the unit would be ohms. Okay, it's the measure of something is ohms. It's the name of it. Okay. So again, Jean-Louis Ampere, Alexander Volta, and Ohm is more from the symbol of it. And the last letter of the Greek alphabet is omega. Okay, so that's where they all come from. Now let's just have a look at a couple of these examples, right? So this is the formula over here on the left hand side, and this is the question. So if I have a 12-volt battery and I have a resistor in series, that means that it's in line with it. A resistor in series of 600 ohms. What is the flow of current? What is the I? So if I wanted to work that out, I put my finger, go back over here to the left hand side, put my finger over I, because I'm looking for I. So that would be, the formula would be I is equal to V over R. So that would be I is equal to 12 volts divided by 600. So that would be I is equal to 0.02 amps. Now again, if I was looking to measure something in the engineering workshop and I was to measure it and it was 3 millimeters, that would also equate to 0.03 meters. But if I asked you what size something was, you'd never turn around and say to me, oh, it's 0.3 meters, sir. And if you turn around to me and said, it's 0.3 centimeters, sir, you'd probably get a stern look. We use millimeters. And likewise, when you're using smaller electronics, we use milliamps, because amps are a big chunk of thing. They're big. So we use milliamps. We're talking about smaller electronics. In electrics, like electrics of houses, we would talk about amps surely, because there's big charge there. Very dangerous current. 16 amp. Your sockets, the plug socket that you plug into the wall, would be 13 amps. So if you touch that, you'd get an awful bad burn, an extremely bad electric shock. You may die. 0.02 amps is not very big. You put it on your tongue and you still wouldn't feel a fizzle. Not that I'm suggesting anybody does that in any way, shape, or form. Do not do that. But we generally talk about it in milliamps. So it's just a different type of unit. We just break it down. Okay. So let's have a look at some practical examples. Here we have a 9-volt battery. Okay, and we have a bulb. And we're going to link the two. So we're going to create a circuit. So the electricity leaves the red terminal of the battery and goes into one side of the bulb and comes out of the other side of the bulb and goes back to the black terminal of the battery. And what will happen when we go up to that, turn it on, to simulate the battery will power the light, and the light will light. Okay, it's important to see here that there's actually, if you look at the bulb, you'll see a little wire between the two. That little wire between the two is a filament. So what happens when electricity flows through certain materials, if they're good conductors, that's grand, it'll flow nice and smoothly. But if it has high resistance, if the wire has high resistance, it doesn't like it. So it's the same as when you take your hands, put them together and start rubbing, you'll generate heat because of friction. Similarly here, when you put electricity through this material, which is called tungsten, tungsten gets very angry when it finds electricity going through it, gets very red in the face, and goes very hot. And that's why light bulbs, when you touch them, can be hot, and they're very, very bright. So that anger towards electricity is translated into heat and light. Okay, so that's basically what happens there. Let's put a few more components in there. Let's look and see what happens when we put a switch in. Okay, so we take the same thing here. We link the red terminal of the battery to the positive terminal of the battery, put it onto the switch. What's going to happen? Well, I'm going to take that switch and I'm going to basically use that switch as a drawbridge. So if I was a medieval knight and I didn't want anybody to get into my castle, I lift my drawbridge. Similarly here, if I have the switch open, okay, the electricity can't flow through. So if everything's on there, it can pass through. So I'm using that to basically switch, create a break in the circuit and turn it on and off. Okay. So you're basically lowering and raising the drawbridge to let the electrons walk into the castle, which is the battery. Okay. So that's pretty much that. Now,